I'm going to give you a high-level summary of what the presentation is going to be. This is great because in case we don't get through it all, this is basically everything that's in here. So when we're learning off policy, which is learning about one way of behaving while acting in a different way, we're going to take different actions than maybe the behavior policy or than the target policy that we're trying to learn about would, but we're also going to arrive in different states and see them with different frequencies than we would. So emphatic methods are attempting to counter this by scaling their learning updates in a way that mitigates this difference between state visit frequency. So there's currently two sort of general algorithms for estimating the scaling factor. One is unbiased but high variance. The other is biased but low variance. Each one operates well in different circumstances, but also there are situations we would like to use them where they do not function. So if we can potentially combine them and mix between them, we'll be able to get the best performance of both.
Is one or both of these the existing standard way that you're departing from in your research?
Yes.
Both of them?
One is the follow-on trace, and one is the parametric estimate.
Yeah, I just wanted you to say whether they are the standard method that you're departing from or not, or whether they are your contribution. Which is it?
So follow-on trace is not mine, and the gradient emphasis stuff is not mine, but I'm building on it.
Yeah, thank you.
Extend it further. Yeah, so basically this is a presentation overview. I'm going to zoom through some of it so that we do not run out of time. But basically it's just going to be some background. We kind of need to motivate the problem, and then main results, and then some conclusions and future work. Yeah, so right, so for background, reinforcement learning, most people know what this is maybe, but not everyone. So intuitively, it's a learning to predict and control one's environment through experience. Simplest setting we formalize this Markov decision process. I'm not going to get into that right now. But in practice, we usually don't see the whole state, and there's usually too many states for us to possibly learn about each one individually. So we use function approximation to generalize between. There's two problems that are especially important in reinforcement learning: prediction problem and the control problem. A high-level prediction is making a judgment about how good or bad a situation is based on what the likely future outcomes are. So in the prediction problem, the agent is attempting to learn to predict the value of each state that it encounters when following a policy given afterwards. A policy is a way to assign probabilities to different actions in each state. You can sort of think of it as a consistent way of behaving over time. Yeah. So the control problem is actually to learn a policy that maximizes the value that the agent will receive starting from each state and then following its policy afterwards. So there's a couple of interesting things to be done with this. One is generalizing these signals, generalizing to signals other than reward to determine to better predict how your actions will affect the environment, different signals in the environment. These problems are also general enough to encompass a wide range of applications. So this is sort of why reinforcement learning is very interesting. Some of the reasons it's very interesting. So far I've kind of talked about on-policy learning, where the agent acts according to the policy it wants to learn about, and then it observes the outcomes and learns from that. However, there could be some issues with this. So if we're trying to learn to predict many signals in the environment when following many different policies or learning about different ways of behaving, if we want to do this on policy, we would have to sequentially learn about each policy over time, which can be very inefficient. Also raises problems like, how do I know how long to learn for before switching? So for many applications, this is also kind of an issue. You don't really want direct exploratory interaction with the environment because that could be dangerous, could be costly. People generally don't want self-driving car to just figure it out as it goes. Or medicine, you don't want like a diagnostic system to just sort of try something new. So we can do something slightly different and learn about a target policy that is different from the one that we're that's generating the data or experience that we're observing. So some examples of this that can maybe sort of be more of an intuitive understanding of it is like, yeah, learning to play a video game by watching a friend play it. So they may take different actions than you would, and they may experience different frequencies of different states than you would. So one example is if your friend's really bad, he's going to see the game over screen a lot more than you, maybe, right? So maybe we should correct our learning for that so that we can sort of have a better solution and learn a better policy or better predictions. Yeah, so many off-policy algorithms in the literature correct the different probabilities that the target behavior policies assigned to each action, but not that many try to correct for the difference in visitation of different states that would be encountered under target behavior policies. So a family of algorithms that does do this is emphatic algorithms, starting with emphatic TD. And then, yeah, later we built on this to come up with an actor-critic algorithm that uses emphatic weightings to scale its updates to correct for this difference in frequency. Yeah, both algorithms scale the updates they make to warp the distribution of learning updates towards follow-on distribution, which is distribution of states that would be encountered if the agent were to stop following the behavior policy and start following the target policy before eventually returning back to the behavior policy at some point. So I just want to throw in a little footnote. We can actually recover the on policy distribution if we use specific setting of interest. You care more about that than look at my paper. Yeah, GMLR. Yeah, so just like notation or nomenclature note is that I'm going to refer to the ideal scaling factor as the emphasis. That's not really how it's been talked about in previous works. We talk about in previous works, they say the emphasis, they mean the actual update that's made at each time. So it's not, it's the estimate of the ideal scaling factor. That's how I'm going to use it as emphasis being the true scaling factor that we would like, and then we're going to try to estimate that from experience. I'm going to limit my definition to ETD 0, not including eligibility traces, mostly just for simplicity, but a little bit also because I'm using another mixing parameter called lambda, and I don't want to confuse people with that. So yeah, we've got essentially a couple of algorithms for estimating the scaling factor that we would like to apply to our learning update. So the follow-on trace estimates the emphasis using a recursive scalar trace, just one number. Yeah, basically it is the sum of interests that we have in each state that we visit, and then that will be scaled by gamma, rho, and adding to the next time step. So it's recursive, but it goes backwards in time, which is different from return that we're used to in reinforcement learning. It goes forward in time. This may not seem like a huge difference, but it allows us to do different things algorithmically and gain more information and make better decisions about our emphasis estimates. Yeah. The following trace is very computationally friendly. The one downside is that because it's recursive and constantly multiplied by this important sampling ratio, rho, t-1, the variance can grow with time, which is not ideal for continual learning or reinforcement learning. But yeah, without any sort of horizon or termination. Yeah, so the next algorithm that tries to address some of these issues is gradient emphasis learning. It uses a gradient TD algorithm, specifically GTD2, with no eligibility traces, to learn a parametric estimate of this scaling factor. Uses these update rules, don't worry about them. Yeah, it's complicated. Don't really have time to get into it. So it requires a lot more computation, a lot more memory, and more hyperparameters than the follow-on trace. So that it can have lower variance, but also it's biased from two sources. One is the initialization of the parametric model. You choose a poor guess for that, then your initial estimates are going to be relying on that guess, and that's not going to be accurate. It's going to be systematically biased. So the problem with that is that like that's not such an issue in value function land, but we're trying to use these estimates to stabilize an algorithm and to correct for this discrepancy between state visits, which if we do that poorly can really mess with the algorithm. So this bias can be a bit of a problem. So that's the initial bias. It also has this other form of bias that comes from using function approximation. So if we have a representation or features X that are not good enough to accurately represent the world, then its estimates are going to be biased forever. It's never going to get better. Yeah. So there's strengths and weaknesses to each method. We're going to try to do some stuff to explore these strengths and weaknesses by testing them on simple environments. So the first environment is a sort of contrived counterexample to policy TD, I guess, where essentially there's two actions. One of them is solid action, one is the dashed action. Solid action always takes you to the bottom state. The dashed action takes you to one of the top states with equal probability. You've got the target policy that we want to learn about is what would we do if we always took the solid action. We're going to learn about that by following the behavior policy, which is going to take the dashed action with, majority of the time, 6 out of 7 times, and then the solid action is going to take it 1 out of 7 times. It's a small discount factor. It's just can be helpful as a sanity check to figure out whether an algorithm will do what we want in some specific situations. So if we look at our empirical comparison of these two algorithms, checked this list of different step sizes, averaged over 50 runs. There are 95% confidence intervals, but they're tiny, so you can't really see them. And what we see here is basically the ETD value estimates, the y-axis being the root mean squared value error. So the difference between the true value that the agent could get and the value that it estimates it could get when following this behavior policy and learning about variables. We see basically ETD is slowly diverging, which is annoying. And this alternative algorithm using gradient emphasis to estimate the emphasis and orbits updates is not diverging. It's also not converging to the ideal solution, which would be 0. So it's okay. It's, I guess, an improvement, maybe. I don't know. But yeah, I guess not diverging is a good behavior. So we can test this on another example to sort of sanity check this, because Barrett's counterexample is quite contrived. It's not representative of a natural environment you would ever really see. So instead, I looked at the collision task, which is a small environment that Sina created, one of Richard's former PhD students, which is supposed to sort of take the useful features of self-driving car collision detection and turn that into a small environment where we can actually make some progress on it. So basically, episodes start in one of the first 4 states. They end when the forward action is taken from the 8th state, where the agent gets a reward of 1, or when the turnaway action is taken in one of the last 4 states. So there's a written out the policies. Essentially, we're going to learn about the policy that always goes forward by following a policy that sometimes turns away and sometimes goes forward. So this sort of lets the agent determine roughly how far it is from an obstacle, or how long it'll be before it collides with an obstacle. So this is what's interesting about this is that the features that the agent has shown are not great, meaning several of the features are active for several of the states. So there's some generalization there that maybe we don't want. But this is really sort of a natural setting in the sense that most of the function approximators that we use involve multiple features being active in many different states. So that's sort of a more natural environment, but also small enough we can actually obtain some useful result from it. So on this task, these two algorithms perform like this. So they sort of are reversed in a sense. ETD performs quite well. It quickly gets to a quite low value error and then stays there. Whereas the gradient emphasis learning, it may look that it's actually horizontal, but that's just because it used the best performing hyperparameter, the step size, is the smallest one I checked. So it's diverging very slowly because the step size is so small. Every other setting of the step size also diverges. It just goes up faster. So in this situation, because the features aren't perfect, the bias is so strong that it can't prevent the algorithm from diverging. Yeah. So ideally, we like to get the best of both worlds. One way we can kind of do this is by combining the existing estimators. Just a really simple idea. We add a mixing parameter, we mix between them. Sort of like the first sort of thing you would think of. But it's a little unsatisfying. We've added a parameter, and that's not really good because there's no way of knowing how you should set that before seeing an environment, right? That's not exactly what we want. We want to avoid adding parameters, have the agent learn as much about its environment on its own as possible. So, yeah, it's difficult to know how you would trade off bias and variance on an example without knowing any features of the example, right? So it turns out we can do something sort of inspired by an algorithm that our own professors, Martha and Adam White, came up with several years ago, where they basically decided that they're going to try to minimize the mean squared error of this estimate on every time step without looking at the effect on any other time steps. That's why it's called the greedy approach, because it just looks at the thing that's right in front of it and takes that. So essentially, we have this expression for mean squared error. We can rewrite it as a product of variance of the estimator plus the squared bias of this estimator. Yeah, essentially, we can simplify this a little bit by just plugging in the estimator, and then we come up with an expression for the bias and the variance. Now we can plug this back in, take the gradient of it, set it to 0, and this will give us a solution in closed form for what our mixing parameter should be that minimizes the estimated mean squared error. So I didn't really want to get into figuring out how to estimate variance. This is sort of a project that I did a month and a half ago, and then I had to stop so I can start working on my thesis. So I basically just simplified this. So there's only two terms. One is the square, sort of based on the other, or similar to the other. And we're just going to use regression to estimate them. So really simple, most basic thing you could really do. So this preliminary result on Barrett's counterexample, we have right here in the green dashed line, this is the resulting algorithm. And you can see that it mostly tracks a little bit what the gradient emphasis algorithm is doing, which is good. It's not diverging, obviously, and it's providing comparable performance to the gradient emphasis algorithm. I've also plotted the average lambda that it has determined. I don't think you can really see it here, but it's basically near 0. It should be between 0 and 1, and I think it goes above 1 at some point for some reason. That's not great. Oh, it's because the estimates are maybe not accurate. Anyways, yeah. So you can see that it's sort of learning to favor the gradient emphasis portion of its mixed estimator, and sort of figuring out if the variance is too high and needs to just stop looking at the follow-on trace estimate. So again, Baird's counterexample, not super helpful, so we should try this in another example in collision, see what it does there. So here, this is much more interesting. We basically have, yeah, it's starting out with the gradient emphasis algorithm. This is due to how I initialized it poorly. But then over time, it learns that the variance is not an issue and the bias is maybe more of a problem here. And it slowly starts converging, not as quickly as you want. So there's definitely some things to be improved here. They'll talk about in the future work. Yeah. There's some issues with the estimates. They're not super great, partially because of the really poor estimator I've chosen, a regression estimator for this. The reason it's not great is that the follow-on trace has this variance that grows with time. And if your target for your regression has growing variance, it's going to not be so great. And it's going to sort of have issues the longer you run it. So you can kind of see this maybe with the average mixing parameter, where it starts getting more unstable at the end. So there's some improvements to be made. So essentially, this is the very first step in something that's a little more interesting, I think. So one of the obvious things that I just talked about is finding better ways of estimating these quantities that you can use to determine a better mixing parameter. Yeah. However, we could also just use different ways of setting. Why did I say edit there? Explore different ways of setting this trade-off parameter. We don't have to use this greedy approach. We can use a non-greedy approach. I've derived a closed form expression for that, but it was kind of complicated, so I didn't want to get into it, and I'm supposed to be writing my thesis anyways. So I just sort of pass on that for now. And then there's other things you can do to combine these algorithms, like Bayesian model averaging, where you take the estimates and you take the observed data and you try to figure out what's the likelihood that this data was generated by each estimate. And then you use this percentage chance to make as your mixing parameter. It's an idea that's existed in other literature for a while, but I think it would be interesting to apply it here. Next thing I would really like to look at is more environments, bigger environments, and ones that are more natural in different ways. Yeah. As quickly as possible. Yeah, does anyone have any questions? No, I jumped over a lot. No, we started delayed. So yeah.
What kind of environments do you have in mind that you think will best kind of highlight this?
I want to look at an environment called 4 rooms. Yeah, where an agent has these 4 different rooms. It's a grid world, and it has several different policies to try to navigate to different portions of the grid world. It's going to learn these policies off policy, because that's more efficient. And I'd like to see how this algorithm works on that setting. I think it's more natural, less contrived, but it still has some of the difficulties that would make this interesting experiment.
Early on in the slides, you had 3 equations, H and U and some.
Yeah, the gradient
Can you
emphasis.
explain those 3?
Yes, that's a great idea. Right. So this is essentially using the gradient emphasis algorithm. So what that is it's like temporal difference algorithm. The direction of time is reversed. This top equation is like the temporal difference error, but for emphasis, not for value. You can kind of see how similar it is to the follow-on trace here. Both have this interest term plus this discounted importance sampling corrected prior estimate. In this case, it's the follow-on trace from the previous state. In the gradient emphasis algorithm, it's the estimate, like the parametric estimate for the previous state, the current parametric estimate. And then this is computing an error term by subtracting this estimate of the emphasis for the current state. So then this error term is used in the second equation. Nope, the third equation, my bad. This is GTD2. So in the third equation, what we're doing is we're trying to learn the expected value of this error term using regression. So we have our target, which is this delta bar, and then we have our estimate, of the expected value of this using our H weights. And the X, which is the features for the current state. So we take this dot product. This is a linear algorithm. We're not doing any deep learning right now. Maybe that's something for the future. So H is attempting to learn this expected value of the emphasis error, projected emphasis error. And then that's used in the second equation. The order doesn't really matter here because the indexes mean that we're still using the old estimates from the previous time step no matter what. So U is the parameter vector for gradient emphasis algorithm. Essentially, it's, yeah, it could be, if I'd written this differently, it could be more clearly linked to temporal difference learning, where if you take the dot product on the right hand side and distribute it across, if you were to replace that dot product in the first term with the sample delta bar and ignore the second term that would generate, you would get TD exactly. So the second term is this sort of gradient correction term. It's quite involved what this is doing, I guess. It's trying to turn temporal difference learning into an approximate gradient algorithm by substituting this estimate of expected emphasis error, and using that to sort of ensure that the algorithm also doesn't diverge. There's some more complicated reasons why that is that I'm probably going to get into right now. Yeah, so that's what it's doing.
And what is I? Is it like a measure of uncertainty?
I is the scalar value indicating how interested we are in accurately estimating the value of the current state. So it's
That could be uncertainty.
yeah, I guess. Yeah, I think there's some work that Martin Flisserov from Mila has done on using different estimates for I, one of which is sort of like a measure of its uncertainty. Yeah. So yeah, you could think that what we've done in our journal paper is used it to unify objective functions. So if you're interested in specifically the on policy episodic objective function, you can set I to be 1 for the first initial time step and 0 thereafter, and you'll recover essentially the on policy objective function, the on policy distribution. So that's one way of setting I. Another one is to set it to 1 at every time step. It gives you a different objective function called the excursions objective function, which is a little more appropriate for this follow-on distribution. It's essentially the objective function you would use if you were actually behaving like this follow-on distribution. If you were to be following the behavior policy, learning about a target policy, as though you would suddenly stop following the behavior policy, start following the target policy, and then that would tell you sort of how much reward you could expect to get when operating in that way, which is a little more natural for options or general value functions or the 4 rooms environment. Yeah. There's many other ways you could set interest, but I don't think we have too much experience doing that. Future research. Other questions?
We have one more question.
Online.
You want to read it to me?
No, okay, so let me ask a question. How would GM perform if we went longer in that counterexample environment? Would it work?
In the counterexample, I don't think it would. Simply because the variance is growing and if over time, which means that in our mixed estimator, right here, when we're determining the lambda that we use, the variance is growing over time, the denominator is getting larger, and it's going to be doing that definitely faster than the numerator, because there's not much bias with the or actually not really. Well, yeah. Anyways, The denominator is going to be growing super big, which means lambda is going to go to 0, which means we're going to stay using the gradient emphasis portion of the estimator, and it's going to essentially behave like the gradient emphasis algorithm will in the long term. That's not the case for the collision environment, though, because the variance isn't as much of an issue there. You can see, where are we? There. You can see the rate at which the green dashed line is going down over time is slowing. And you can also see that the average mixing parameter is getting more erratic and possibly growing. I mean, probably due to the poor regression estimate on this quantity that has very high variance. So I would expect this over time to probably turn around and maybe diverge, just because it will be doing a similar thing. If the variance is growing, the denominator is getting larger, and you're eventually going to set lambda closer to 0, which is going to be more like gradient emphasis learning, and that diverges in this example. So I would expect that to happen in the long term. It's nice that that doesn't happen in the first 10,000 steps. That's pretty cool. So if we can find better ways to estimate these quantities, which I'm sure we can, I'm sure they already exist. In fact, I know some of them already exist. I just didn't have. It's explicitly told to stop working on new things, so I stopped working on new things, and I'm working on my thesis instead. Yeah. So this is a good first step, I feel.
More questions? Thank you, Eric.